Thank you very much. Okay, and as Clinton mentioned, I'm the research manager in Hart-Jackson's lab in Toronto, and today I'm going to present to you about whole-slide imaging mass cytometry and how it enables the rapid profiling of tumor spatial heterogeneity and the immune microenvironment. And so in the Jackson lab, we're really focused on imaging mass cytometry technology and how we can really start to push this forward. And I think that some of the talks earlier today have really started to get at this conversation around scaling. And so we have this, our typical IMC workflow here, but then how do we sort of take that to the next level? And we think that being able to scale, and that's more tissues, more tissue areas, more samples, and it's really important for us to really understand and be able to capture all of the heterogeneity that makes up the disease complexity. And so versions of this slide have already been shown today, and so really I'm just trying to illustrate that we all know that the advantages of metal isotope tagged antibodies over their fluorescence-based counterparts, and so really what we're trying to say is that advantage is really in that difference for us. But when it comes to the lab and when you're making decisions about what sort of techniques you're going to use, it's really about the questions you're trying to answer. And so it comes down to, do you need to do something like immune profile, where you're going to need up to 40 parameters in order to get all the subpopulations you're looking for? Then you're really going to be looking towards something like IMC, and that's going to allow you to get all of those parameters, but in a tissue-restricted area based on that 1 micron rasterization. If we look at immunofluorescence, because we can tile together fields of view, we're able to do much larger tissue areas, but we're going to have reduced dimensions. Maybe we're only doing 2 or 3 antibodies at a time. So it really depends on what type of questions you're asking and the trade-offs for both. Now, advancements in SciSif or other multiplexed immunofluorescence methods, now all of a sudden we can do multiple rounds of staining, and so we're getting more parameters across that large area. But at the same time, we've had engineering advances with IMC, and so we've gone from that 200 hertz Hyperion to the 800 hertz Hyperion XDI, and so now we can actually do much larger areas in less time. So with advancements in both, why are we sort of pushing this scaling in terms of IMC? And so really what we see the advantage here is that IMC allows us to get those high-plex images while still maintaining the tissue integrity. We don't have to worry about immunofluorescence or tiling together, tiling issues or focusing issues. We also have, because we're doing it all in one cocktail, we're doing one pass on the IMC, we're also limiting, tissue processing damage over time. It's highly quantitative. We get low channel spillover if we're titrating our antibodies. We actually know how much tissue we're measuring. We have that high linear dynamic range, and we don't need that spectral deconvolution. With every technology, obviously, there's going to be some challenges. You need to have a mass cytometer or have access to one. The conjugation chemistry is always going to limit how many markers we can look at. Currently, that chemistry is getting us about 43. We are limited to that 1 micron rasterization size, which is what's making it slower to acquire these large areas. And obviously, the technology is destructive, so it can't be combined with anything after the fact. And so when we think of scaling multiplexed imaging, we see all of the benefits, all the advantages of using this technology, but when we want to scale it to more tissue, bigger tissue, it's important to kind of put that into context. And so what are other technologies or other things that are done at scale, and what kind of things can we learn from them? And so if you look at the clinic, it's really the H&E, kind of the gold standard still. And it's not just what information you can get from the H&E, but it's also because it's fast, it's reproducible, and it's cost effective. And so if we're looking to scale multiplex imaging, we have to keep all of those types of things in mind in order to kind of push it forward. And so if we want to do future applications, how do we translate multiplexed imaging? Well, the first is to kind of keep in mind how would it fit into a clinical workflow if that's where we want to see it in the future. There's that aspect of sample quality control. We also there needs to be a purpose, not just because we can do 40 markers, but what are we getting from those predictive panels, spatial biomarkers. There's also this key component of standardization. If we're going to scale, how do we make sure everything is reproducible? And then finally, there's the throughput and speed, which Clinton just alluded to. How do we increase those two things to kind of translate this even further? And so we still think that imaging is the right modality. There's no sample loss. You can do smaller, rare samples. There's no dissociation. You can do biobank tissues. We think that IMC is the answer because it's a one-stain cocktail. You can do simultaneous marker acquisition, and also ultimately there's stability in that tissue stain. And so I presented this last year when we were introducing the work we had done with the Hyperion XTI. And so if we're looking at speed and throughput and how do we scale, the reason we want to do that is because we want to make sure we're getting the maximum amount of information we can from the tissues that we're looking at. And so this is a 1 centimeter by 0.6 centimeter ROI acquired on the XTI. And basically we're just using it to illustrate how much information you're missing if you're just doing a TMA core or a biopsy. Yes, you can see that there are immune cells in those two areas, but you can't really tell how localized that immune infiltration really is. And so if we zoom in on these two regions, you can really see that in some areas, you have very small amounts of infiltration, and in others you have, basically the whole ROI is dominated by the infiltrating immune cells. And so, these getting us bigger is getting us the information we really need in order to understand the complexity of whatever it is that we're looking at. The other thing with that speed is that how quickly can we turn around results? And so this was a pilot study that we had done with Dr. Kieran Campbell's lab at the Lunenfeld. And so basically we wanted to see how quickly we could return results. And in this pilot, we did immune profiling of a liver metastatic biopsy from a patient with pancreatic cancer. And we were able to go from samples to single cells in less than 36 hours using a rapid pipeline for automated analysis that Kieran's lab has developed. And so we know that we can go faster with these biopsies, but we also know that we're not getting the information we need. And so if we go back to those advantages I already talked about, it really is that 1 micron rasterization and how fast we can acquire the tissue. That's kind of the thing that's limiting us currently. And so how do we fix that? And so if I go back to that large image, that was only part of an actual slide. The actual whole tissue was larger than that. And it took 20 hours to acquire. So we're probably looking at only being able to get through, even on the XTI, a few whole slide sections in a week. If we look at biopsies, we know we're missing information, but we can also do way more across that same amount of time. So how do we rectify this? How do we get these whole slide sections faster? And so the answer really is to change that rasterization size. And so we already saw that in Clinton's video, that the new tissue mode increases that from 1 micron to 5 micron. And that's going to allow us to go about 25 times faster across the same area. And so that's hopefully going to be able to take us from what was this to many more whole slides across a single week. The second thing is how we interact with the machine. We just saw the slide loader, so I won't go into detail about using this, but we've been lucky enough to be testing this with standard biotools, and so this basically allows you to make sure you can get through overnight or get through the weekend without someone having to be physically there to change slides, which for those of you who have run it know they are always at an inconvenient time, whether that's 2 a.m. or on a Saturday when you'd rather be somewhere else. And so what does this look like? Now, we saw this image in the video. I have to tell you that we put together, this was our largest piece of tissue we had. We put together a small panel and stained it and sent it to Standard BioTools for acquisition. And I wanted to make sure the staining looked good. And so I pre-ablated a small ROI at 1 micron just to make sure everything looked good. And now this image haunts me because it's out there with this pre-ablated square that I just wanted to make sure everything looks okay. But I'm framing it that that was a really good idea because now I can zoom in and I can tell you what those two different areas look like. So I did it on purpose for a good reason. But at 5 micron, we can see that you sort of lose that ability to tell where one cell ends and the next begins. You can't really see the cell borders, but you can still see the overall structure. You can also still see all of the immune cells that are infiltrating into that region. If we zoom back out, you really get an idea of what the overall immune infiltration looks like in this tissue. For the original purpose of why we had this tissue, we had a few ROIs that looked like they had strong levels of immune infiltration, but when you look across the whole tumor, you can see that that's very localized. We have a sort of stable area on the left, and then a highly infiltrated area in the center. If we zoom in again, you can see what the T cells are looking like at 1 and 5 micron, as well as what a tertiary lymphoid structure looks like at 5 micron. And so, we know we can scale, but what is the use case for this? And so we also had a separate project. I have a separate project in the lab that's running, looking at the proteomic characterization of high-risk prostate cancer. And so there are a lot of parallels between these two. This is a large cohort. It's only 42 patients, but it's actually 125 whole slide sections. And across those, there's 181 pathologist annotated ROIs. And so this is part of a multi-site study where everybody is responsible for acquiring all 181 ROIs and in their entirety. And so the objectives of the study are actually to try to figure out the differences between Gleason pattern 4 and Gleason pattern 5 histologies. And so for those who aren't familiar with prostate cancer, we have this sort of staging system where it's either referred to as the Gleason score or the Gleason pattern, but we're specifically, no matter what score, looking at the high-risk cases. And what we see is that there's a lot of heterogeneity in terms of metastatic rates or overall survival within those categories. And so we want to look deeper and see if we can figure out the proteomic differences between these two Gleason 4 and Gleason 5 histologies. We also want to be able to look at tumor and non-malignant tissue and see what the changes are happening there. And then we want to take all of those features we find and we want to see if they associate with clinical measures or outcome data that we have for these patients. And so, we have 40 to 50 ROIs per group. And this project really started out like every other project in our lab, putting together a panel. This is kind of a very diverse panel. We have an immune and metabolic focus, but we also have prostate signaling markers. We have extracellular matrix in there. We have a lot of things. And then we went through the steps of actually validating the antibodies there on the right. But then the project really had come to a standstill. And that's because the average ROI size is about 4,500 by 4,000 microns. And I have to say, we actually agreed to do this project a really long time ago. And I'm pretty sure Hart left out some pretty key details, because when I went back and I did the math, and we only had a Hyperion, it would have taken me 218 days to acquire this whole data set. I felt a little bit better about it when we got the XTI, because it was like, okay, 54 days, that's better than 218. But it's also 125 slide changes across those 54 days, so it still has me kind of living at the lab for 3 months. And so at this point in time, we started to think about, well, maybe this is the application for the 5 micron acquisition. What would it take for us to acquire these regions with a slide loader at 5 micron? And the answer is approximately 3 days. So I obviously thought that this looked way better. But at the same time, it's like, we could do 4,500 by 4,000 microns, or we could do everything. And so the decision was made that we would actually do this on the entire tissue section at 5 micron. And I can tell you, we started this study in February, and it took us 42 days to acquire all 125 samples. And if you're wondering how that math translates, essentially people were getting PhDs faster than I was going to get through all of these samples. So I'm very thankful for the 5 micron and the slide loader. And at this point, before I show the data, there was, if we think back to that, scaling and what else we need to keep in mind, there's some things that need to be done when you're scaling to this large level. We need to make sure that it's reproducible and that, there is an element of cost effectiveness there. We've already, we fixed the fast part, but we still have these other 2 things to keep in mind. And so the first thing that really became clear was that, we don't have an autostainer. Chris mentioned earlier, if the robot's broken, use a PhD student. I'm not a PhD student, but this was the backup plan here, as there's no automated way of doing this. And so we realized that we were going to need to split this into batches. And so the first thing we were going to do with that is we're going to need to freeze the panel. And so we ran a quick pilot study where we ran 4 serial sections, frozen panel 1 week, 12 weeks, or 24 weeks. And then we looked at all of our markers across that time course and saw that we had pretty consistent mean pixel intensities across it. There are some examples where we did see a bit of a drop-off between the 3 and 6 month time point. We weren't overly concerned about this in terms of our study, because the idea was for it to never be frozen that long. And in reality, it only was frozen for 14 days. But this is something to keep in mind as we go forward. The second thing was, we talk a lot about stain stability, but what does that really mean? If we were going to acquire this over 218 days, some of those slides are sitting there a lot longer before acquisition than the initial ones. So how stable is that stain? And so I don't like to throw anything out. So I went through many of my slide boxes, found the oldest thing that we had in the lab, and then reacquired that. And so there's about 3 years in between these two acquisitions, but you can see that the staining quality remains excellent on these slides. I like to say that they were well cared for during those 3 years, but in reality, they've just been thrown around my desk for 3 years. And so even without being well cared for, we still see that nice stain stability. So the jump to the 5 micron also added another level to it. There are other things to consider. The one thing we know is we're getting more tissue into the machine. So how does that impact the amount of antibody we need to use? And so what we did is we took a titration series we had previously run at 1 micron, ran 5 microns on the unablated tissue, and then compared the mean pixel intensities. And you can see that they're significantly higher in the tissue mode acquisition. And so Standard BioTools has gone on to actually quantify this, and it's about 10 to 13 times greater signal. So typically in the lab, we're in the final concentration range between 1 and maybe 2.5 micrograms per mil. But this made it clear that those mean pixel intensities were so high, we were going to need to scale back for the titration. And so this is just an example with LDHA, but you can see I've actually started this titration at 0.5 micrograms per mil and worked my way down. And then if we look across all of the antibodies in my panel, I actually ended up using, on average, 0.32 micrograms per mil as my final concentration. And obviously, this kind of gets to the cost effectiveness point. We're not talking about cost effectiveness in terms of comparisons to other technologies, but cost effectiveness comparing IMC to itself. Obviously, this would be a lot more expensive and require a lot more antibody had we actually done this at 1 micron. So what does the data look like? I really understood the title of the last talk because 125 whole slide images is a lot of data. It's overwhelming. Where do you start? I'm also not a computational biologist. And so what I'm going to do today is I'm going to show you examples from one patient. And so this one patient had 4 different samples in the cohort that are across the 4 different histologies. We have benign intraductal carcinoma, Gleason pattern 4, and Gleason pattern 5. And if we look at the immune content in these sections, we can see that we're seeing different infiltration patterns into that pathologist annotated region across the 4 histologies. I think the kind of take-home message here, though, is that there isn't a lot of immune infiltration. And from what we know about the prostate tumor microenvironment, that's not exactly surprising. Where we really start to see the spatial heterogeneity is when we start to look at metabolic markers. And we're seeing that heterogeneity not just in the pathologist annotated region, but across the entire piece of tissue. And so this was really important for us because had we actually done this acquisition at 1 micron, we never would have noticed that. We've also looked at heterogeneity in the signaling markers. And again, we see that across all 4 histologies. And we also start to see some loss of prostate-specific markers in the different histologies. So I'm sure the question out there really is, how do we analyze this? And for the question of, can we segment this to get single-cell data? The answer currently, right this moment, is no. We haven't been able to segment the data. What we're doing is we're taking different approaches and seeing what we can adapt in order to work with this 5 micron data. And so we obviously have 40+ localized measurements, and we want to know things like how many CD8 T cells are coming into my particular region of interest. And so work by Kate, who is a graduate student in Kieran Campbell's lab, has started to adapt some of these spot counting methods to this question of 5 micron data analysis. And so what you're looking at here is her counting CD8 positive T cells across this entire tissue. The second thing we've been doing is clustering the data. I can tell you this work is being done by Darren, who is a graduate student in both the Jackson and Campbell labs. The sheer size of this data is sort of the first thing you need to tackle. There's about 20 to 25 million pixels per image. So when you're trying to do pixel-based analysis across 115 slides in this analysis, that's a lot of data to process. And so nothing happens fast is kind of the first thing. And so what we've started to do is actual working on these pixel-based methods to cluster our cells. And so this is an example of this. What I can say is this is very much a work in progress. This experiment finished running at the end of March. it's the beginning of May. And so we're just starting to apply these methods. And Darren here is specifically using Starling, which is a recent preprint from the Campbell lab, looking at an algorithm that does segmentation error aware to kind of help tease apart those markers where you still have something on an edge where you have a CD4 and a CD8 T cell together. And so that works well with this 5-micron data. So in the last couple of minutes, I just want to introduce something that we're really excited about that both the Jackson and Campbell labs have been working on together. With all of these new data sets, we need new ways of being able to visualize and analyze these samples. Obviously, everything is much bigger, but I still want to be able to use all the features that my normal visualization software has, and I want new features. And so Matt, who is a software developer in both labs, has been working on a solution to that. It's called Rakaya, and it allows multiplex image analysis in the browser. And so what I'm going to do is I'm just going to take you through some still images to give you an overview of what Rakaya can do. The first is visualize. I used all of the images in this presentation. They were all made in Rakaya. And so these are large files of a single ROI. And so it's a lot to be able to even do simple things like change markers and change colors. And so Rakaya has really enabled me to be able to do that with these images. It gives me all the features that I want. I want to be able to scale. I want to be able to choose my markers, choose my colors. But it also has this channel gallery where I can basically just scroll through all of the different channels in my panel and take a look at what the data looks like kind of on the whole before I select any markers to my canvas to make my images. This obviously is not just going to be for 5-micron images. We're doing this with 1-micron images as well. And I'll get to a little more detail about what's going on in this image in a second. But basically, we're also have this data set viewer. And the important thing here is if you have multiple ROIs in your experiment, and you want to be able to look at them all at the same time, this would allow you to turn on certain markers to look at them and then scroll down and see all of your different ROIs at the same time, saving you from having to download TIFFs or trying to remember what patterns look like between ROIs. So if we go back to this image, another key thing we want to be able to do is annotate. And so this annotation and quantification kind of go together. So in this image, what you can see is we've actually annotated the duct here on the left. But what we're also looking at here is we're looking at the segmentation masks overlaid on top of the image. So you can take your masks, upload them into Rakaya, and then actually be able to check your segmentation. This is all working towards that point where we can quantify. So you can actually upload, say, your measurements file from your panel output, or your file output, and then you can actually project that onto a UMAP, do your channel expression, look at your channel expression across different markers, and then you're actually able to go back and look at what that looks like in the data. Finally, there's the report feature. I really like this one. If you have collaborators, someone you need to share the images with, TIFFs are great, but sometimes they're not the easiest way to do that. So within Rakaya, you can actually download an HTML file that you can send to your collaborators for them to look at the image. Also, if you're a student or a postdoc and you've ever received this message, because your PI doesn't actually have the software to open it, you can just send them the HTML file and they'll be able to look at it themselves. The nice thing about this HTML file is it's actually dynamic. So if Hart had wanted to zoom in on a particular region and see what was going on, I don't need to go back and make him another image. He can just actually do that within the HTML file itself. And so your channel markers are going to be locked, your colors are locked, but they can actually still interact with the image. And so this is coming soon. If this is something you're interested in, if you'd like a preview copy, please reach out to Kieran Campbell so that he can discuss that with you. So with that, I just want to acknowledge all the members in the Jackson lab, Hart himself, and then Matt, Darren, and Gulnaz, whose work I showed today. I also mentioned his name a lot, but our collaborator, Dr. Kieran Campbell in his lab at the Lunenfeld. This is also, like I said, part of a larger group project, so the whole prostate proteomics team. And then finally at Standard BioTools, I want to acknowledge Nikesh and Nafisa, who actually ran the 125 samples for me and had to deal with all of my questions and constant need for status updates. Thank you.